Okay, we're going to start this lesson with a little bit of a review. The concepts we're looking at are reciprocals of linears, which is this one, and later on we'll look at reciprocals of quadratics. So the instructions are to sketch each of the functions and then describe the intervals where the slope is increasing and the intervals where it is decreasing. So we start with our standard approach by identifying x-intercepts, y-intercepts, vertical asymptotes, and horizontal asymptotes. The x-intercepts are found by setting y equal to 0, and in this case we have 0 is equal to negative 2 over x plus 4. When we attempt to solve this, we simplify to get 0 is equal to negative 2, which obviously does not exist and is not a true statement. So that tells us that there are not any x-intercepts, and we can go ahead and what we can do is we can place our horizontal asymptote located at y equals 0. And we label it y equals 0. 0. The next thing is to take a look for is the y-intercept, and that we find by setting x to be 0. So y is equal to negative 2 over 0 plus 4, and we see that this simplifies to become negative 1 over 2. So we can place that at 0 and negative 1 over 2. Moving along, the next thing we want to find is the vertical asymptote, and the vertical asymptote is found by taking the denominator, which is x plus 4, setting it equal to 0. Therefore, there is a vertical asymptote at negative 4 because x cannot be negative 4. Let's go and sketch that. Again, these are not to scale. If it was, that point should probably be up a little higher. And I need to state that x is equal to negative 4 is the equation of that line. We already have the horizontal asymptote. There it is right there. So we're ready to sketch. So when we're looking at this graph, we know that from this point, as it approaches, the vertical asymptote, it will hug that line continuing all the way down, and we also noticed it will hug the horizontal asymptote. We have a mirror image on the opposite interval. That's a sketch. What we want to do next is determine where the slope is increasing and decreasing. And when we're talking about slope, one of the ways is to represent the slope with lines. And so I'm going to choose a point, and I'm going to sketch a line at that tangent point. So for example, I might start with this point and then draw a tangent line right at that point. And then what I might do is I might write out what the slope is. So I'm just going to make up slope. I know it's positive because it's moving up to the right. Let's say it's a slope of approximately 2. Then I might pick another point farther to the right. Remember, we always read from left to right. And now I might state that this is still a positive slope, but it's steeper, so it might be a slope of 7. Well, that's enough. The numbers are going up. That means that between negative infinity and negative 4, the slope is increasing. And we would take a look at the next interval again. You can take the line approach. It's a very steep line. Say this has a slope of 10. And as we keep moving to the right, this might have a slope of 3. And as we keep moving, this has a slope of maybe a half. Well, we're going from 10 to 3 to a half, which is decreasing. So therefore, we would say from negative 4 to positive infinity, we have a decreasing slope. Let's take a look at another example. This one is a reciprocal of a quadratic. We can identify the denominator with a quadratic. What we need to do in this case is go ahead and find things like the x-intercept. Once again, we plug in 0 and 1 over 9x squared minus 6x plus 1, and this simplifies very quickly, becomes 0 equals 1, which once again doesn't make sense. So at this point, we've recognized that all reciprocal functions will have a horizontal asymptote located at y equals 0. So let's jot that down. Here we are, and y equals 0. The next thing to look at is the y-intercept, and I'm going to solve that just by looking at my main function and canceling out the x's. So the y-intercept is located at 0, 1, and then we would look at the vertical asymptote. So this one is probably going to involve some factoring. I've got 9x squared subtract 6x plus 1. I'm going to use that trial and error method, which is just a shortcut. I need to develop a middle term of negative 6. So let's try 3 and 3 and 1 and 1. If I cross multiply, 3 times 1 is 3, and 3 times 1 is 3 this way. I need to make a negative 6 here, as we have in the middle. So both of those need to be negative. I need to make a negative sign in front of the 1, negative sign in front of this one, and then add some x's. And there are my two factors, which, as it turns out in this case, is exactly the same factor. So if I were to factor this, the factors are 3x minus 1 times 3x minus 1. So this tells me that there's a vertical asymptote at x is equal to 1 over 3. And I would sketch that line at 1 over 3. I would plot that y-intercept, which is located at 0, 1. And then what I need to do is I need to take a look back and determine what those end behaviors are. So I'm going to take a look at what happens as x, let's do it over here, as x approaches negative infinity. So once again, as I put a very large number in here, negative, it's going to square and become positive. Multiplied by a very large negative number, which multiplied by negative is still positive. So I know that this is 1 divided by a very large positive number, which moves closer and closer to 0. So there's a point there. As I approach positive infinity out to the right, the same thing occurs. Now I do subtract off, so if my answer, my x value is a trillion, I'm going to square a trillion and multiply it by 9. Then I'm going to subtract off 6 times a trillion, and that sounds like a pretty big number too, but as the larger number goes, the squared overpowers everything else. We kind of ignore the rest. And I end up with the same idea as I had for the left-hand side. It will approach 0 from the positive. So this graph is going to look a little different than other graphs that we've graphed, in the sense that it has that kind of, we talked about it, that little Atari symbol shape. And so you end up with a sketch that looks something like that, and a sketch that looks something like that. Once again, we can talk about the slopes. If I take a point right about here and I draw a tangent line, the slope is definitely positive. And I notice the slope's getting steeper. When that occurs, the slope is going to be increasing in this interval. If I look at the next interval, I have a steep negative slope, like negative 10, then about a negative 5, then a negative 1/2. Well, negative 10 to negative 5 to negative 1/2, those numbers are going up, so I would say that that would also be an increase in the slope. So you really have to look at these independent. Those are two good examples of reciprocals. Now we need to move on to some questions that we started in 3.3, and that is looking at a true rational function. We, again, go through the same criteria, looking for the x-intercepts. The x-intercept is found by setting y to be 0, and when that occurs, the denominator eventually just gets multiplied by 0. And we end up with 0 is equal to 4x plus 5. Now once again, here's a little hint. And the hint is that when I'm finding my x-intercept, I can look solely at the numerator, and that will find it. So as I solve this, I find out that x is equal to negative 5 over 4. So I have an x-intercept at negative 5 over 4 and 0. Y-intercept is found again by getting rid of the x's, and the y-intercept is 0 and negative 5. The vertical asymptote is found by taking the denominator and setting it equal to 0. And that eventually simplifies to x is a half. So I've got x-intercept, y-intercept, and vertical asymptote. The last thing to find is the horizontal asymptote. And we saw in the last lesson that the horizontal asymptote can be found when, in fact, the exponents are the same by taking the leading coefficients of both and dividing. So the horizontal asymptote in this case is y is equal to 4 over 2, or just simply 2. We can now sketch this graph and have a better idea of what it looks like. So let's start with our horizontal and vertical asymptotes. The horizontal asymptote is located at 2, so that we're now not at 0 anymore. And the vertical is that x is equal to a half. I'm going to go back and label those. Y is equal to 2, and x is equal to 1 half. We also have some x and y intercepts. The x-intercept's at about negative 1 1/4, so negative 1 1/4. And the y-intercept, I believe, was at negative 5. So again, this can give us enough information to figure out where the graph is going. It has to run through these 2 points, so it's coming fairly steep, and then bending near the horizontal asymptote. The same idea comes from the top. And again, you can always plug in values or points to check. So there's our sketch of a rational function. If we are asking for things like domain and range, domain is everything except for the vertical asymptote, and range is everything except for the horizontal asymptote, so you can write those out. You can now continue and answer all kinds of questions. So looking at the intervals, it may ask you a question about, is the function f of x, is it increasing or decreasing in which intervals? So the first interval, the y values are going down, so we'd say it would be decreasing. In the second interval, the y values are also going down, so it's decreasing as well. That's asking you about the increase or decrease in the function. If it's asking about increase or decrease in the slope, then maybe you want to draw some lines. We see that the slope is moving from negative 4 to negative 10. That's a decreasing slope in this interval. And if we look at these, we are running at negative 10 to maybe negative 5 to negative 1 half. That's an increasing value because negative 10 to negative 5 is going up. So all of these can be looked at. I'm not going to look at instantaneous rate of change, but we know from the previous unit we could plug 7.5 into the x values and find out what the y value is, and then because it's instantaneous, we may choose a value of 7.501 and substitute it in and use the slope formula to help us find the instantaneous rate of change. There are a couple special cases that we need to be aware of when we're dealing with these. So when we're dealing with these, we have this particular situation where we have an exponent on top that is bigger than the exponent on the bottom. And something interesting happens in this case. We still find the x-intercept the same way by taking the numerator and setting it equal to 0. and we see that x is equal to plus or minus the square root of 2 over 3. 2 over 3 that's supposed to be. The y-intercept is found by hiding the x's, and we see the y-intercept to be negative 2, so 0 and negative 2. The vertical asymptote is still found the same way, and we can see that it's equal to x is equal to 1. Now the horizontal asymptote is where things get interesting. In the previous lesson, we took a look at some of the rules that we had when we were dealing with asymptotes. And what the rule said was if the degree is less than m, then you have horizontal asymptote y equals 0. That's our reciprocals. If the exponents are equal, then you have a over b. When n is greater than m, there is no horizontal asymptote. And what we need to do then is to go back to something we haven't touched on in a bit, which is use long division. And long division is a way of determining where that asymptote is going to be. We know it's going to be what we call an oblique or slant. So it is going to be a linear, and this is how we do it. We take our divisor of x minus 1 and we long divide, and you could use synthetic division here, but long division is probably quicker. We have to use a placeholder, and we just continue. So x times negative 3x gives me negative 3x squared plus 3x, and then we subtract. We bring down the 2 and negative 3. Now, long division only needs to be done until you get to the point where you've multiplied your last term. The quotient is in fact going to be our oblique asymptote. An oblique basically means a slant or a diagonal.
Alright, let's take a look and plot the information that we have. So we have a y-intercept at 0 and negative 2. We have x-intercepts located at the positive square root of 2 over 3 and negative 2 over 3. And we have a vertical asymptote at x is equal to 1. We also have a oblique asymptote at the equation of line y equals negative 3x minus 3. If we were to find the x-intercept of this equation to graph it, we would set y to be 0, and we would end up with 3 is equal to negative 3x, and therefore x is equal to negative 1. So that would be about that location. And the y-intercept is simply 0 and negative 3. And that would be about here. So we would take and draw an asymptote between those 2 points. And I'm just going to extend this slightly here just to show what actually happens with the asymptote. So that line gets extended and this line gets extended. We're now ready to sketch the curve. We do have these 3 points, and what ends up happening is we end up with a sketch that looks something along the lines of that, and the same sort of mirror image down below. So all of a sudden now we are getting different shapes that fall into wherever the asymptotes are. So these are fairly unique sketches of polynomials, but this occurs once again when the exponent is higher than the exponent on the denominator by a difference of 1. One last special case we want to take a look at, and that one is once again involving a special situation. So in this particular situation we have a quadratic divided by a linear, and this looks as though the last one did, that there will be an oblique asymptote. But something happens when we factor the numerator. The numerator factors out to be x minus 3 and x plus 2. We have an x plus 2 on the bottom, so before we graph anything, we would like to simplify, that's a 2, by canceling out these entire factors. And what we're left with is basically an equation of a line that looks like y equals x minus 3. Now when we graph this or plot it, we can tell that the y-intercept is at negative 3 and the x-intercept then would be at positive 3. And we end up with a straight line, and I'm actually going to draw this by hand. We end up with a straight line running through these points. But something happened up here with the x plus 2, because when we look at restrictions, we know that x cannot equal negative 2. So what we have to do is we have to find x equals negative 2 and where it intersects with our line. So if I take negative 2 and plug it in for x, I have negative 5. So the coordinate point right here at negative 2 and negative 5 actually doesn't exist. And so what we do is we draw a little open circle to indicate that the function is discontinuous at that point. And this is called a hole in the function. And because of the restriction, we have to account for that. So the rule that we have is when you're dealing with any type of polynomials, make sure you factor them first. If something cancels out, then you will have what we call a hole. So this is definitely a special case.